converter. In this lecture, we'll see a little bit on analog to digital converter or AD. For example, let's say you have a heartbeat of human heart, which is typically a 72 beats per second or 60 beats per second. If you try to place your heartbeat on a graph grid and try to take samples or points where exactly it crosses the vertical lines or the y-axis lines. If you consider this particular grid and you try to point, as the grid being not that deep or like not that fine, lines are a little bit apart, and if you try to put the points and try to connect them back, you'll be able to see a signal which is not exactly same as the input signal. That means the reconstruction is not proper. And take the same signal now and you take a graph which is more precise, which is having too many number of points. So you try to point out this, take out samples of each vertical line, be able to sample it very much properly. Which means even if you remove your input signal and try to plot joining the lines, you'll see a much precise and much perfect ECG signal. This is what we call as reconstruction. So the main aim of the ADC is to convert an analog signal into a digital equivalent, so that it can be reconstructed back also. The main important terms when you see about ADC are like what is the input signal frequency and what is the sampling rate of the ADC. Because if suppose your input signal frequency is around 100 Hz and if you sample at the same rate as like we have done in prior in the example shown, you will not be able to reconstruct it properly. So for which we have to follow the Nyquist rate. Nyquist rate says that the sampling rate should be 2 times of your input signal frequency. So with which you'll be able to reconstruct the analog signal back. And one more important parameter is the resolution of ADC. That means how many number of bits you are using to represent your analog signal into a digital equivalent. For example, a 10-bit ADC is there. The final like maximum value you can go is like 2 power 10 minus 1. So it's like around 1024 minus 1, 1023. Now we shall see a little bit on ADC math. For example, your V reference is 1 volt and V input is 0.5 volt. And you have a ADC which is having a resolution of 10 bit. So maximum value you can go for is 2 power 10 minus 1. It will be 1023. Sorry for the typo. And now finding the digital equivalent. How would you find out a digital equivalent? You'll just divide your input with V reference and you'll multiply with the full scale. You'll get the equivalent digital value. And how would you find an analog value? That is the same. You can do the reverse math, where you divide your V reference value by your total values which can come, which gives you the precision of a single bit. And you multiply it with the digital equivalent, you will get the input voltage. Coming to ADC pin of node MCU, the ADC pin on node MCU is exactly located on the left side of your PCB antenna, which is named as A0. A0 is the name given on node MCU board. Now if you see the schematic of ADC input, how it is connected to the A0 pin, it's like the A0 pin input will be coming to ADC external. Through a voltage divider, it will go to the T-out pin of ESP8266. Now ESP8266 has an input voltage range of 1 volt only. Because of this voltage divider, you can increase it to 3.3. Because even if you give an external voltage of 3.3 volts, because of the voltage divider, it will get divided by 100k by 100k plus 200k. This is a normal voltage divider formula. As fraction of input voltage will be going to the ESP8266 board. Now coming to what kind of ADC is inside your ESP8266. Successive approximation register type ADC, which mainly contains a sample and hold circuit, comparator, a DAC and SAR. DAC is nothing but a digital to analog converter, which give you at an analog value. When an input comes to sample and hold circuit, it will be sampled at a rate and it's given to comparator. DAC gives you out an approximate digital approximate value. DAC gives you an analog input. Now this analog input and your actual input are compared at the comparator. It's given to SAR. Now SAR checks whether the comparator value is nearby to the digital value or not. If it is nearby, it will stop comparison. If it is not nearby or which is greater, it will increase the digital value. If it is lesser, it will decrease the digital value. Based on increase or decrease of digital value, you will get a corresponding analog value. Now again it is compared with your VN. Now after a few approximations, you will find the proper digital value. Yeah, as like in the previous project, I just created a new project and imported machine, and in the main loop I've created a module in which the main loop has a while function, while true. It's a continuous loop, an infinite loop. From the machine module I utilized a function called ADC. I just mentioned which number of ADC. ADC 0, and I just try to use this ADC object dot read, which will give me out what is the ADC value which is currently at the pin. Now I'll just run it. I see some problem. No Python interpreter. No Python interpreter. Support requires 3.5 SDK. Maybe my PyCharm did not actually catch the interpreter because I have updated my PyCharm. Yeah, now it's okay. Yeah, they are gone. Now let me run my program. Yeah, everything is fine. I was able to do it. Now let me open my putty. Node MCU. Yeah, I'm seeing a value 1024. Why? Because I have connected the node MCU in such a way that the A0 pin is directly shorted to 3.3 volt. Now let me see some other thing. What I'll do is I'll just remove it and connect it to ground. I just removed it. Now the pin is floating. You can see some garbage values coming in as because the pin is floating. So it will be like numerous analog values will be at the input. Yeah, now I shorted it to ground. Still I am seeing a minimum value. This is the minimum value that it can be measured, I think. Hope this explains you very well to how to use the ADC which is on board for your analog sensors. Thanks.